This posting appeared on the AirSpy mailing list in August 2017. It's about a loop antenna made from a coaxial cable. This image is a bit hard to understand, but it is like this. I follow the current from one side of the transformer through the center conductor over to the screen, and then through the screen, and here the screen black is the same here, so the current continues here into the center conductor and back to the transformer. The midpoint here is connected to the screen of the coaxial cable. Here we have 50 ohms. Here we want to have a very low impedance, so the drawing for the transformer is a bit misleading. Few turns on this side and more turns on the secondary. The coaxial cable is grounded at the midpoint, so the air gap on the screen is on the opposite side of the grounding point. So this thing is balanced. An electrical field that comes vertical is not going to introduce a current through the screen of the coax. But any non-vertical electrical field coming in from the side is going to cause interference, because a capacitor in here creates a current here, and that will couple to the loop and generate a voltage on the transformer. We will see more about that later. Here is what it looks like. I'm using an RG213 cable. The diameter is 30 centimeters. And the transformer here has a primary winding which is a single turn, and it's a single turn of a very thick wire that I made from some copper foil, and I have tuned the primary with a 6.8 nanofarad capacitor in series. The secondary is 17 turns to provide something in the order of 50 ohms. Means that the impedance of the coil is 17 squared times smaller than 50 ohms. Here is what I can see on the spectrum analyzer. The impedance is 50 ohms on 1.09 megahertz. The standing wave ratio is of course then 1, but only 20 kilohertz away the standing wave ratio is 50. So it is quite narrow. This is a filter, more or less. Here is the arrangement. The loop is now horizontal, and here you can see what it looks like on the top. I changed the frequency scale a little bit, because now I will show what happens when we place an aluminium foil on the loop. Like this. You can see how the bandwidth increases and the frequency gets higher, much higher. And of course the sensitivity to radio waves has disappeared completely. I mean, the sensitivity to magnetic fields. The sensitivity to electric fields is probably unchanged, because I haven't connected this aluminium foil to anything. Here is the top of the loop again. I hope it will be better visible. I screen off some of the light because I don't know how to manage the camera and its automatic features of brightness and focus. The time is 1 hour past midnight. I'm listening to an English station on the loop antenna. And you can see the S-meter graph. There is some QSB. I will now switch to a 10-meter long wire antenna. And as you can see, the level is about 10 dB higher. But looking at the noise floor out here, now it is about 40. And I go back to the loop antenna. And you can see the noise floor is not only 10 dB lower, it's 20 or maybe even 30 dB lower. So there is an advantage with the loop in its interference suppression as compared to the wire antenna. That's on this frequency of resonance. Now I'm listening about 45 kilohertz lower. This is the wire antenna, and I switch for the loop antenna. And as you can see, the level is now about 20 dB lower. So the useful bandwidth with this antenna used in its tuned mode is quite narrow. It is a filter. This could be an advantage in some situations, but probably for most people it is not going to be a very good idea. I now remove the capacitor and change the turns ratio to 3. Means 50 ohms divided by 9. That's about 6 ohms to load the loop. What I see on the network analyzer is like this. Standing wave ratio is not so high anymore over the medium waves. It's about 10. And you can see the impedance here. It's far from resistive, but it is about 50 ohms here. So this is optimum to run it untuned on the medium waves. Now I'm using the loop without tuning, and it's on the station that was on resonance before. And you can see the signal level, it's about 30 or maybe 40 on the dB scale. And I switch for the wire antenna. And you can see here it is at about 65 maybe, 35 to 65, that's 30 dB. But there is some QSB, so I will have to switch it back once more to really compare. Now about, well, this is a QSB down. And now it stays here, so I switch again. Not the right cable. So this was the wire antenna again, and the loop antenna, and it looks more like 25 dB, the difference, 20 to 25 dB. But now, as you can see, the spectrum is more flat. And of course, the noise level, well, I don't know really what to say about it. I will listen to some other frequencies to see. This is about 700 kilohertz, and this is the wire antenna. And here is the loop antenna. And it looks like something about 30 dB worse. The proper way of using a loop is with a low impedance amplifier. I don't think you can see it so well on this video. It's a very simple thing with a small battery. This is the schematic diagram. More turns here makes the frequency response go further down in frequency. It's feedback, so this turn here is seeing the virtual ground point of the gate here. And then the current through the FET is stepped down by a factor of 10, 20 turns to 2 turns. I haven't optimized it, I just took something. Because without the transformer, the current is going to be too small for a 50 ohm load. This is the magnetic loop. I'm listening to this English station at 1089. You can see here the stations and the noise floor. And the loop is turned to maximize the signals from England. And you can see the level I have here. Now I will change to the wire antenna, the electric sensor. As you can see, the signal level is similar. I can't say whether it's stronger or weaker, but the noise floor, up here at least, is not as favorable. It's hard to know about the noise floor. Well, no, it's not hard. You can see here the noise floor is much higher. I will change the gain of the baseband waterfall, 0.25, say. So it will be easier to see signal levels. And it's obvious we have more interference on the electric sensor. This signal is a little bit stronger on the wire, probably because the loop is not aligned to this station. This is 252 kilohertz on the wire antenna, and you can listen to the interference. Of course, I can adjust linear to suppress interference better. For example, by making the attack time longer here, and the hold time shorter, and also release time. But this is some kind of standard, what you will find in most receivers. And you can hear there is interference, and you can see it on the waterfall. The signal level peaks at about 50 on the dB scale. I now switch for the loop. This is still the loop with the amplifier. As you can see, the level is about 12 dB lower. So I changed the 0 point by 12 dB. That means 8 here. Remember what this looks like. And here you have the noise floor with the same scale, and you can see it is far more quiet. And probably you can hear that through the microphone of the camera. So even though the signal is weaker, the signal to noise ratio is better. And with a simple amplifier we can do better, and it could be a good idea to make the loop a little bit bigger than 30 centimeters. I think this video shows that a 30 centimeter loop, if you want it to run as a wideband antenna, needs an amplifier. If you tune it, it will work without an amplifier with a good sensitivity. I mean, reasonably good. And that is a good option if you want to listen to some particular station on medium waves. Then a small loop that is tuned for that particular station can be a good idea. If you want a wideband, untuned and passive antenna for medium waves, it has to be bigger. I would guess 1.5 meters, maybe 2 meters or so, to get a decent sensitivity. Still not a very big thing. It could be fairly easily accommodated in most QTH. This is the loop antenna near 1.5 megahertz. There is a station, or maybe a couple of stations on this frequency. And you can see the level and the noise floor. And now I switch to the wire antenna. And the signal level is the same on this particular frequency because the loop is oriented properly for this. It's probably from England. But you can see other stations became much stronger. And also, as you can hear, the noise is worse. Crashes of some kind. I don't know why this happens. I mean, the electric fields and why these crashes are not present as magnetic fields. It's interesting. But it seems with this simple amplifier, this loop is better than a whip on medium waves. And note that these antennas are now installed without any chokes on the cables and without any normal protection from conducted interference. So it could be possible to do much better than this. But I'm not so sure because these crashes do not belong to signals from inside my house. I don't think so. It's electric fields of some kind that are not accompanied with magnetic fields of the same order. And I don't understand, but I can observe this, and I will have a look a little bit closer to it when I get the time, because the phenomenon that I observe does not agree completely with my theoretical thinking about interference and medium wave antennas.